Good morning. Thank you, Mr. Chairman. Thank you, the participants. I see that we haven't had that many casualties after last night, so it's good. I hope I don't bore you in the morning. The topic of my talk is design for additive manufacturing, some methodologies to enhance the fatigue properties. We will review some ideas and some of the results from our previous research. Before starting the presentation, I would like to thank my PhD students and master students who helped me with this research, Morten, Liam, Alf, and Loker. Here you see an overview of my talk. I will start with some relatively boring facts about AM. In the second part, I will review a few tailoring techniques to enhance fatigue properties. And in the last part, I will show you some of our recent research on one of those tailoring methods. Well, we are in Additive Manufacturing Conference. Everyone knows what benefit it has and what limitation it has. But one of the main three important points for AM and its benefits is its increased design freedom. We can produce parts that were not possible to produce before. We can make consolidated parts. So instead of making assemblies, we can make the parts in one piece. And there is potential for lighter, more materially efficient component. But how can we reach these goals? We need an effective design procedure. And so far, there has been some ideas, but reaching to a solid technique has not been reached yet. Let's review another aspect in AM, scalability. So different researchers with different AM techniques, they have been producing AM parts in different scales. Some examples for metallic parts are shown here. This antenna, for example, it has been produced with laser powder bed fusion in microscale. Some structural nodes in centimeter scale that have been produced with the goal of reducing the weight of the components. Or larger structure, for example, this propeller, or the 12-meter bridge that has been fabricated by MX3D. But in different scales, how do we evaluate how is the performance of the component? How do we check the reliability? If you look at the literature, there is numerous articles evaluating mechanical properties of AM parts under static, fatigue, corrosion. And they are mostly based on the standard procedures that are provided for conventional materials. And there is a good reason for it, obviously. We want to compare our results with conventional material. But one of the most common techniques is we have our main component, and in order to evaluate its mechanical property, we just print some coupons in the same print next to the main component. If we want to make it a bit more precise, we print those coupons in different directions. We print them with excess material to do machining. But I have a question, what can be the problem with this technique? If you look at the geometry of this main component, which is a connecting rod for automotive industry, it has quite different geometry than the tensile samples that we are testing. And it has quite different size and diameter. Okay, we wanted to see how this size and scale can affect the mechanical property. In the first step, we saw this parameter in 1D, meaning thickness. Very simple. The material was titanium grade 5. The fabrication technique was EBM, and we considered three thicknesses, 1, 3, and 5 millimeter. So you see the range is not even large. This is a work we did 4 or 5 years ago. After fabrication, we checked the microstructure. You can see in each row, you have one thickness from 1 to 5. If we compare the grain size of these three specimens produced with the same feedstock, produced with the same process parameter, and in the same batch, we can see going from 1 to 5 millimeter thickness, the grain size is approximately 3 times larger. And this is the median size. the maximum is even higher. Why is that? If we look at this schematic picture, we can see the larger the part is, on average, during fabrication, the temperature will be higher, and it will remain higher for a longer time, even though the energy density is the same, meaning that the grains have a longer time and a higher temperature to grow larger. What can it do to mechanical properties? We performed some tensile tests on this. And we could see that from 5 millimeter thickness to 1 millimeter thickness, there was 11% increase in strength and 73% drop in elongation. The same thing was done for conventional titanium. The difference was 2% and 7%, 1/10 of what we saw for AM. Similar type of test was performed for fatigue. We could see that from 5 millimeter to 1 millimeter thickness, there is 27% drop in the fatigue properties. Okay, so clearly there is an impact on mechanical properties based on the scale that we had. Another simple case. We wanted a simple way of checking the geometry effect, a V-notch. It was printed, very classic, you all know. Overhanging areas will give higher roughness. But let's look at the microstructure. This time, within the same component, we see a significant gradient of microstructure, something we usually neglect. If we see the top part of the notch, we can see that the grains have grown quite larger, similar to the effect that we saw for the thickness. But again, why is that? In this case, for the case of notch component, the top side of the notch has a lower cooling rate because the consolidated part underneath is quite limited, and transfer of the temperature, transfer of the heat through the powder is quite less than a solid material. This will result a higher temperature on the top side of the notch, resulting in grain growth and ultimately leading to a gradient of microstructure and local different mechanical properties. Okay. It's quite common to say bad things about AM, challenges. How can we overcome it? Let's look at this complex geometry. Most of the research in AM field is on effect of something. Effect of DC treatment, effect of printing speed, effect of heat treatment. I can make an unlimited list for this. And then we do the test, we see the effect, okay, it's a publication. But in real life, what we want is the other way around. The industry comes, they say, we want this component. You decide which parameter you have to say. How can we do that? We need big data. And it's easy to say it. It has been a key word among researchers to talk about machine learning. I'm going to bore you with that in this slide. So a large number of experiments is needed. This can be microstructural, defect, mechanical properties, and this can be gathered, but they are expensive. So a common way to facilitate this is to use numerical modeling and couple these two. And what is important is not to treat this as data only. There is a link between them. So if someone wants to have a physics-based predictive tool, they need to have a proper physics-based link between those variables. Ultimately, the data from these two batches can be fed into a machine learning procedure based on proper modeling tool, linking the microstructure to the mechanical properties. We can have a predictive tool for a final product to set what is the requirement for its fabrication. Okay, let's draw two preliminary conclusions before I head with the rest of the presentation. If we want consistent AM parts, we need variable process parameters. As long as you use constant process parameter, you have to expect the variation that you see in the microstructure. Besides that, we saw that the microstructure can very well be determined or linked to the thermal history during fabrication. So why, instead of having this unexpected gradient, we manipulate the process parameter to get the gradient of microstructure that we want. That leads me to the second part of the talk, tailoring techniques. Of course, the first tailoring technique that I would like to talk about is microstructural tailoring. Consider this simple case. I've taken this from my lecture, so it's the easy case to say it. A simple plate and a plate with a semicircular notch. We have stress concentration at the edges of the notch. Those are the sources for fatigue initiation. And in fatigue, we know finer grains are favorable for the location where you have expected crack initiation. On the other side, when we have fatigue crack growth, coarser grains are more resistant. So what we want is a microstructure that is fine at the critical locations, coarse, where the crack is going to propagate. One way to do that is to vary the process parameters point by point, a point cloud technique. There is no single optimum process parameters. The people who work with process optimization, they are very familiar with these matrices of laser power and scanning speed. We have multiple cases, multiple process parameters that you can indeed use and get fully dense material. What is the difference between them? Their microstructure. Some will give you coarser microstructure, some finer. So the idea is to have a combination of these processes, these parameters, to get this gradient and have finer grains where we want, coarser grains where we want. What's the challenge there? It's quite difficult to program this for an AM machine. It is already difficult to perform it even with the process parameter that we get from the company. Now you want to change it point by point. Second, there are limitations, software and hardware, to perform this. And you need to get the agreement from the AM company that you have purchased the machine. So we are quite early stage here at this type of tailoring. So we thought of another technique. What if we just print the shell? If we have a 3D component, we print the shell and we leave the bulk material as powder. It's kind of cheating. But you do this, what you get is an empty, well, not quite empty, but a structure that is filled with powder after printing. You can, of course, expose this component to hot isostatic pressing that would pressurize the inner part and sinter the inner powder. There are also numerical predictive tools for how the geometry will turn out after this process, so you can actually incorporate it in your initial print. This will save both time and would expectedly give us a gradient of microstructure. So we checked this. We had shell structure, typical specimens for fatigue testing. You can see one of them was printed solid, the other one was shelled. They were both exposed to HIP, standard HIP, we didn't change it. The standard HIP that we use for titanium, same parameters. You can see also there is some shrinkage on the shell sample. Then we did microstructural evaluation. We could see, okay, around the shell, after annealing, we had the basket width microstructure with quite thin alpha grains. Going towards the inner parts, we had more of an equiax microstructure for this titanium sample. And the grain even got coarser when it was in the middle of the sample. We had a challenge because we didn't, we either have this direct joining of the two material, or we have gradient path, which is more common for directed energy deposition. There, the mixture is being blended step by step, and we get this gradual change from metal A to metal B. Or we can have an intermediate section with 50-50% volumetric of the two material in the middle. There are few works on this. People have printed titanium and copper, cobalt chromium, or copper and inconel, and few other works. What we try to do, of course, this is super preliminary, so it's hard to show anything. we try to use a second material where we have the critical regions in the component. You can tailor it very simple, just a steel, and have high strength steel where you would like, and high ductility steel where you would like. And the process is being set with heated printing, so you don't need to do heat treatment afterwards. And the ultimate part that you can get can have the favorable fatigue property. This is a work we are performing with University of Strathclyde, and our preliminary data have shown an improvement in the fatigue performance of the parts. So this was quite short. Let's go to the third method to improve fatigue life. Geometrical tailoring, designers like this. Less of material and microstructure. Again, the same old classic example of semicircular notch. How can we reduce the stress? The answer is simple. Change the geometry of the notch. That's what we do in topology optimization. And sometimes people put some boundary condition effect to have a control in this change. We reduce the stress concentration factor and ultimately get the better mechanical properties. But how to reduce the stress concentration factor? By a minimal change in the outer boundary of the component. How can we keep this outer boundary the same? We don't want to remove so much from the bulk material to get a better stress state. How do we do it? We will check. So in the first part of the idea, we thought, okay, some odd idea. You have a notch component, you want to improve its performance, you add more notch to it. It works, it redirects the stress flows in the component and would result in lower stress concentration factor. We did some preliminary work on this in different arrangement of this added notch, and the results were relatively promising. We could see that the fatigue life under that specific load was increased by a factor of 2 to 3. But let's be honest, it's not a clean way. It's not a designer's way to drill some holes. It doesn't seem practical. So we looked for a more controlled way. We thought of incorporating lattice structures instead of those holes. So we include lattice structures in the solid component. We manipulate the stiffness of the component, keeping its outer boundaries the same. This is very much similar to any functionally graded structure that you can see in nature. So some people like to call it nature-inspired. Yes, okay, nature-inspired. We consider two control cases, semicircular and elliptical notches. And in the elliptical case, the larger diameter is 3 times the smaller one. We designed some functionally graded lattice specimens, or it's better to call it tailored specimens because it has solid parts as well, with the same geometry as the elliptical case. In this case, the lattice was having a relative density starting from 25% to 100% and from 50% to 100%. So 4 cases so far, the 2 control cases and the tailored samples. Then in order to eliminate and minimize, that is the correct word, minimize the boundary condition effect, we added a 0.5 millimeter thick shell around that lattice to make its interaction with the notch bisector line to a minimum level. Okay, so we have 6 cases now. The samples were designed for fabrication. They were fabricated with V4 photopolymer resin using SLA technique, stereolithography. They were out of this material with the mechanical properties that you can see, and then tested using an Instron machine. At the same time, we performed some simple stress analysis to see how is the stress varying. As expected, we could see that the stress at the component is being reduced. Not to the elliptical case, obviously, but lower than the semicircular specimen. We had around up to 30% reduction in stress concentration factor. Then we performed mechanical testing. First, static. If you look at the semicircular notch, we can see that we have a localized strain, localized deformation, something that me and my colleagues in fatigue and fracture love it. That's why we go for localized failure criteria. On the other side, for the elliptical specimen, the deformation is quite uniform, like a smooth specimen. That's where the global methods work. So what we wanted with this technique, we wanted to get as far as possible from this localized nature to more a load transferring in a global. If you compare the pictures that I'm showing here, the controlled specimen and the tailored one, you can see that the distribution is quite similar. Let's see what is the effect on mechanical properties. Of course, the goal was not static loading. We just wanted to see if it gets any worse in static. But we could see almost in all cases, the failure load was increased. Then we look at the broken specimens. The specimens that didn't have that shell, they had the failure all the time within the lattice part. And obviously, this was shown in our elastic plastic analysis that it was showing the highest plastic deformation within the lattice part. For the specimen with the shell, the protective shell, we could see that the main point of criticality is remaining on the notch bisector line. Okay, we perform fatigue. This plot is a bit messy, so I'm going to separate it. First case, the Taylor geometry with a relative density starting from 25%. Two cases we had with shell, without shell. The case without shell, which is the solid red line, the fatigue properties actually got worse. We added so many edge effect that was detrimental. But the case where we included the lattice structure with the shell, we could see that there is a significant increase in fatigue life. We had an increase of 200% and 500% in the mid-range fatigue life. And of course, in the fatigue limit, it was hard to measure it because of the run-out samples. The failure in most of the specimen was happening at the mismatch point where the stiffness was different, where we had the solid part and right next to it, we had 25% relative density. So of course, we knew that this is something to work on. In the second batch of specimen, we had 50% relative density. The improvement was less. Obviously, we are removing less material from the design. So we expected that we get less improvement. Overall, this tailoring technique can be an efficient way for the design that we are making for our parts. We could clearly see an extension of fatigue life in the mid-range up to 500%. Of course, for this specific material, again, it's a polymer. We are working on metallic samples at the moment. The level of these local stresses at the notch root of this tailored design, it very well is dependent on the morphology of the functionally graded part of the sample. If we look at it, there are some parameters that needed more study instead of randomly selecting it. The partition shape, the gradient orientation, the relative density, and the boundary conditions. So these are the things that needs further evaluation. Plus, this was just an actual tensile test. How about multi-action? Of course, that's a bigger challenge. How can you select that? So we knew that, okay, it is not quite possible to do this manually. And we came to this is my last slide, I promise. We came to this idea of a point cloud technique for relative density. We don't design solid structure anymore. We have a component, we consider it's 100% lattice. Where we need it to be solid, we just simply place relative density equal to 100%. Where we don't want it, we change it. And how do we decide where to change this? We have developed this optimization technique to give us the best possible relative stiffness in the component, as you can see in the contour. And then we correlate this stiffness, which is ranging between 0 and 1, to the relative density, depending on the morphology of the lattice that we choose. And then we can have this component, the notch component that you can see down there. Even though it has solid parts, it fully lattice structure. Thank you for your attention. If you are interested on this subject or you would like to discuss it more, I would be more than happy to be in contact with you. You can scan the QR code and get my contact from there. Thank you.